Hello and welcome back. Excuse me. So in the last video, we were looking at Tukey's honest significant differences, and we were able to get a pretty elegant kind of output here. We were able to get the mean difference between the pairwise comparisons here. We were able to get a p-value telling us if the difference is statistically significant, and then we were able to get a 95% confidence interval for the difference in means that we can blow up to apply to the population from where these two things came. Okay, excuse me again, sorry. What we're gonna do now is we're gonna talk about another type of post hoc test, okay? So you do the ANOVA and then you do some kind of after the fact kind of test, okay? And this one is by this guy, Bonferroni. He's an Italian economist, pretty cool guy. And he was able to kind of figure out a method of doing pairwise comparisons after doing an ANOVA. And the whole idea here, or at least his whole idea, is, how about instead of doing some really fancy math, why don't we just take our alpha that we have, which is usually 0.05, and then divide it by our number of tests, number of hypotheses or comparisons that we are using, okay? And that is how we are then going to compare our new t tests that we're going to do, okay? Now, that was, way back in the day when you're doing things by hand, and this is pretty simple, okay? The downside to this is that our alpha, our kind of new alpha, is going to be, it's going to shrink down very quickly. And let me kind of show you just from a calculator point of view before we get into it. So let me do it in the script. So we're moving on to some Bonferroni stuff. So usually our alpha is 0.05, okay? And then we compare our p-value to that, okay? But the more comparisons we're making, the more likely it is we'll make a mistake. The more likely it is we'll see something totally random, some big difference, but it's due to randomness that a normal t-test can't really account for. We may make a mistake. Another way you can view p-values and alpha is essentially the percent chance that we're making a mistake. We're making a wrong comparison. So the convention is, we're okay with a 5% chance of being wrong, essentially of making a mistake in saying that there is a statistically significant difference between whatever things we're comparing. But when we're doing a bunch of comparisons, we're more likely to make a mistake. So we got to correct for that. So what Bonferroni said was, okay, well, if we are, let's say, doing 10 comparisons, so our alpha is always 0.05, but we're making 10 comparisons. Okay, if we run that, and this is just a calculator at this point, our new alpha is going to be 0.005. Okay, so I'll just go ahead and kind of put this 0.005. So then the t-test that we do, we have to not be below 0.05 for our p-values, but we have to be below 0.005 to make a claim that there is a statistically significant difference, okay? Already you can kind of see where this is going. The more comparisons we make, let's say we make 20 comparisons, that's a lot. Our new alpha really shrinks down to 5. It shrinks down super, super fast. Now, I don't think we've seen a p-value this low before, and we will see p-values that are really, really, really tiny, okay? But so far we haven't. And already, this is being pretty strict, okay? So to say that there is a statistically significant difference when we're making 20 comparisons, well, that's when we actually have to be below this value, okay, rather than the normal conventional 0.05. Okay, so this is what's happening in the background of what I'm about to show you with this Bonferroni correction. Okay, so we don't necessarily have to do this math. The math is built into the function, which is great, but that's essentially what's happening. Okay, now the con, again, the more comparisons you make, the stricter this test becomes. Okay, sometimes that's a good thing, but sometimes it's bad. It's not it's not as lax as Tukey's on a significant differences. And we'll get to more why I like this Tukey the most. Anyway, so we have this function called let's see. Yeah, here it is, pairwise T test. Okay. I did forget the name there, to be totally candid. But when I typed in pair, it gave me a bunch of similar kind of things, right? And we have a bunch of different options here, but I want the pairwise T test. Okay. Now the thing about this function is that it's kind of awkward, I think. It's not as elegant as the single line for Tukey's, and it requires kind of a lot of information too. So if I hit tab here, it'll give me all of the options, all of the arguments in here. We'll just go ahead and go one at a time. X is going to be our response variable, our outcome, and we actually have to grab from the data this time. We are not grabbing from the model like we did with Tukey's. Okay, so that's going to be weight. That's going to be weight. And we also have to use $ notation in this case. It's kind of, I don't know, it's kind of janky, I think. And then what do I hit next? Well, if I hit tab, then it'll say, okay, X is already taken, so I need to fill in the next one. And G equals, we see that the yellow box here says grouping vector, okay, which is just, or a factor, which is just our grouping column, okay, which in that case is the only thing we have left over, and that's diet. Oh boy. And then the next thing we need to put is this p.adjust.method. That's kind of a long argument name, but we'll go ahead and do it. p.adjust.method. I hit tab there to fill it in for me. I don't know what to put in here. And when I'm confused about what goes into an argument like this, I'm just going to type in a question mark first, and then the function name, Pairwise T Test. And if I hit the old control enter there, I get this little help menu here. Sweet. So then it says method for adjusting p-values, cp.adjust. And we can come down here. Let's see. No, I guess I'll click on the old hyperlink. Cool. Then p.adjust.methods, we see that it gets these three things. Okay. Holm, Hochberg, Hommel, Bonferroni, BHBY, FDR, none. Okay. Oh, geez. So that's a lot. Already we can see how many other of these post-hoc comparison tests there are. And this is still a fraction of the actual. So I want Bonferroni. I'm going to do a Bonferroni correction here. So I can just grab everything that's there, including the quotation marks, control enter, or control V to copy and paste. And then if I run this, it takes a second. I think my computer is starting to really kick it. Cool. Okay, nice. Now let me see if I have this. Let's see. Yes, here we go. It's a little closer, right? So what is it telling us? What is this output telling us? Well, the first thing on this first line, pairwise comparisons using t-tests with pooled standard deviation. Don't so much worry about this little bit of information. Worry about what it's actually doing. And it's doing t-tests, okay? But it's also correcting for the fact that we're making a bunch of comparisons. In this case, it's using the Bonferroni because we specified it too. If we type in none in quotation marks in there, it will just do every combination of t-tests, okay? But we don't want to do that. We want to make sure we're not making any false claims about anything. And so in this case, these values that are in this nice kind of like matrix here are the p-values, okay? Not exactly the most, readable, but what are we looking for? Well, it is already doing the adjustment for us. We don't have to do any math to make a new alpha. We don't have to make a new comparison value. We're still comparing at 0.05 in this case, which is cool. Okay, so these p-values here are already adjusted for us. Okay, and what conclusions can we make? Well, since the p-value for this one is below 0.05, it's at 0.02. Well, we can say there's a statistically significant difference between these two groups. Are there any other statistically significant differences? No, there are not, which is consistent with our Tukey's on a significant differences test as well. Here's the bummer, though. This is all it gives you. Okay, you have no access, or at least no easy access, to getting a 95% confidence interval for the differences. It doesn't even tell you what the mean difference is between these two groups. You have to go in and run, let's see, this again, right? And then do the math there. And then you have to by hand calculate the confidence interval for that difference. And if you're not about that, like I am, because I'm not about that, that's kind of a pain in the ass, honestly. So does this test, tell you the kind of basic conclusion? Yes, that the whole population of rats that eat beef with high protein are going to be statistically different than the rats that eat low protein from beef. Okay, and that's all it tells you, is that these two populations are different, or at least these two diets in our sample. We can blow it up to the population and say that they're different. And then these groups down here, these comparisons, so cereal with high protein and beef with high protein, not statistically significantly different. And then same is said for all these other ones. In fact, these p-values, this is the biggest a p-value can ever be, is exactly 1. And so we're very certain that there is no difference between these three pairwise comparisons. Okay. Now, I don't like this, to be totally honest. Just because it's not accessible, it answers a single question and does not give us the same information that this did. This is wonderful. I think this is really great. Whatever, though. You may have an advisor or a boss or something in the future that says, can you do a Bonferroni correction test on our ANOVA model? Well, then you say, yeah, sure, I'll just do this. And then you have to go through a couple more hoops to get the same information that Tukey gives you. Okay, and I'll make a comparison between these three tests at the end here, just so you can kind of see when to use what and why you would maybe want to use this instead of something else. And with that, we'll go on to the last type that I'll show you. And we'll just kind of go from there. Again, you can choose to do any of these. Tukey's is my favorite. And also, the conclusions we make are the same as we saw with t-tests. Okay, so when you're at this point in the post-hoc comparison, you do not so much have to worry about adding more language or anything to your repertoire. You just have to apply the same stuff we learned in t-tests to this. Okay, with that, we'll move on to this false discovery rate, and I'll see you there in just a second.